Hello, how are you doing, everybody? Sorry, I'm a little close to the start time. My student, they had to make cables today, and I was just trying to help them before the network class. Okay, so check out the lab that we have to do, which is going to be a little bit more number conversion. And then we'll start in a minute. Okay, so today we are going to work on hexadecimal, binary, and completing a little bit more arithmetic. Okay, so give me a second. Let me go into screen share. So where we left off on Tuesday, last Tuesday, we touched on subtraction after we completed addition. So right now I wanted to go over multiplication for binary, and then a little bit of hexadecimal conversion. You can also refer to your class notes, which contain the main concept as also your assignment. So right now what we want to do is we want to cover the binary multiplication. This is the only lab that we're not programming. Starting next week, your Thursday lab will be in C++. So we wanted to just understand how to do number conversion before we start programming, okay? All right, this is page 5 of your notes, and your notes goes over binary multiplication. If you look at the example, it's going to be very close to what you've seen in decimal number multiplication. So we would first start with looking at the rules for binary multiplication. 0 times 0, we would get the output of 0. 0 times 1, we would get a 0. 1 times 0, we would get a 0. And 0 times 1, we would get a 0. And then 1 times 1 is a 1. So for this example, we have 1, 0, 0 times 0, 1, 1, and these are in binary. Then we would start with the rightmost digit, which is this one right here. And we would take 1 times 0, we get a 0. 1 times 0, we would get a 0. So you're going to move, you take the bottom row and you multiply it by the top, and you're going to go from right to left, okay? And then we are going to take this 1 times 1, we're going to get a 1. Then we move over to the next digit on the left. We're going to take 1 times 0, we get a 0. 1 times 0, we get a 0. 1 times 1, we get a 1. And after that, do we need to multiply the 0? No, because anytime that you multiply the 0 to anything, as our multiplication rule here, we would get a 0. So once you have the digits multiplied out, then you want to add them. So the 0 simply drop down, and then this 0, 0 plus 0 is 0. 1 plus 0 is 1, and then 1 plus 0, because the top would be a 0 there, is a 1. So your final result is 1, 1, 0, 0. Okay. And the same example is shown in your assignment. So let me see if I can find my whiteboard. Let's do, let me erase this. Let's do the first question together, and then you can do the second one on your own. Okay, so, sorry, let me close all these notifications. All right, so we have, we're gonna do 1A right now together. So we would start with 1, 0, 1, 1, 1, 1, 0, and we would multiply that. And keep in mind that these are in binary. We would multiply it by 1, 1, 0, 0, 0, 1, 0. So you want to start with this one first. And we're gonna make it multiply by each one of these as we go along. So 0 times 0 is 0. 0 times 1 is 0. 0 times 1 is 0. 0 times 1 is 0. 0 times 0 is, this is a 0. 0 times 0 is 0. And 0 times 1 is 0. Then we move over to the next digit, this one. Then we have 1 times 0 is 0. 1 times 1 is 1. 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 1 times 0 is 0. 1 times 1 is 1. So as you move to the left digit here, you also want to move to the left digit as you place it as the result. Okay. Then we are going to be now at the 0. So we would then, you can simply 0 multiplied by anything is going to be 0. So 1, 2, 3, 4. 0, 0 times 1 is 0. 0 here, another 0, another 0, 6 and 7. Okay. Let me see. I'm going to run out of room there. So we can place the next 0 because there's 7, 0. Okay, as we multiply that out. And then the next 0. And then you just multiply the 1. Let me rewrite this on the top. So okay, and then the next is going to be over 0. Okay, and then another set of 0. Another set of 0. And then we are going to move now into the ones and we're going to add it up. Okay. So 1 times 0 is going to be 0. Oops, sorry. 0, a 1, a 1, a 1, a 1, because it will be the same. And then the same for the other one. 1, 2, 3, 4. Zero and a 1. Then after that, you would add everything up. Okay. So this 0 would just straight chop it down because that would be in the same thing with those. They become the 0. So I'll write that on the top. And then a 1 plus a 0 and another 0 is going to be a 1. 0 plus a 1 plus a 0, 0. That's going to be a 1. Same thing with the next one. Same thing with the next one. Same thing with the following. Now, when you get here is where you need to do the carry. Okay. The 1 plus a 0 and a bunch of 0, that's going to give you a 1. 1 plus 1 is going to be a 0 with the carry. 0 plus 1 is a 1. Then this carry, we will continue. So you handle the top numbers first and then move downward. So a 1 plus a 0, you add these. So that's going to give me a 1. A 1 plus a 0 is a 1. A 1 plus a 0 is a 1. A 1 plus a 1 is a 0. A 0 with the carry. A 0 plus a 1 is a 1. So now this carry, we're going to again do 2 numbers at a time. 1 plus a 0 is a 1. A 1 plus a 0 is a 1. A 1 plus a 1 is a 0 with the carry. A 1 plus a 1 is a 0 with the carry. A 0 plus a 0 is a 0. Then we are left with the 1 plus a 1. That's a 0 with the carry. So just like what we did with addition, you have to operate the addition using two numbers, get the result, use that number and move it down to the next line and so on. Anytime that you have a carry, you got to bring it to the left column and apply it to the left column as you add them. Okay. So when we take these two and we add them together, this is our result. And if you wanted to be specific, you can say that's a base 2. Okay. Question. So for the test and quiz, right, and also future references for other class like assembly, you would need to know how to do a binary arithmetic. And like I said, you can always use a programmer calculator to check your work. So that would be another option for you to double check. Okay, so that would be 1A for the lab 1 this week.
Professor Gwen?
Yes.
I'm sorry, just for where the arrow is, I know that's where I think that's where things started changing. Would you mind just going over just that particular column one more time? Because I missed how we carried over
Yeah.
to the next line.
So let me take this out. Okay. That's a 1. So the rest on the right, we just drop it down. Let me
Right.
switch pen.
Right.
So we would start with the top 2 first, right? And so we would say, okay, a 1 plus a 0 is a 1. I put a little 1 there, so I know a 1 plus a 0 again is a 1. A 1 plus a 0 is a 1. And then a 1 plus a 1 is a carry, right? It's a 0 with the carry, and then a 0 with the 1 is
So
a,
what is the answer under the line then? Because we carried, oh, it's a 0?
it's a 1.
Oh, it's a 1. Okay.
Yeah, because at this point you have a 1, right?
Okay. I see. That's where I
And
missed.
then and then the carry, then you're gonna do it again
That's on the
here.
next side. Okay.
Yeah.
Got
So
it.
a 1 plus a 0 is a 1, right?
Thank you.
Yep. Yeah, sometimes it's gonna get like a little crazy when you handwrite it. But I always put a little 1 next to what I'm adding, so that, or like right above it, then I would know. And then the carry, I just move it over to the next one so I don't get confused. Okay. Yeah, so when you take a look at that column, the next column is exactly like it, but so then you have a carry to the left of it with the 1, and so on. Other questions? Okay. All right, I'm gonna do B, just because we don't have that many to do for the lab anyway. So let's do B. Okay, so let me clear this. All right. And this time I'm gonna write a little smaller. So let's put the whiteboard next to it. Okay. So we will do, and this is 1B. Okay. It's 1 1 0 0 0 1, and then 1 1 1 0 0 0. And we're gonna multiply. So we're gonna start with the 0 here. Okay. Then we're gonna do 0 plus 1. Everything is gonna be a 0 there because you know the rule. Anytime you multiply the 0, it's a 0. Okay. And then the same thing with the next 0. Okay. And the same thing with the next 0. Then we would take the 1, multiply it by the right here. So that's going to give us 1. And it will be 0, 0, 0. 1 times 1 is 1. 1 times 1 is 1. And the same thing to the one on the left of it, this one. So you would have 1, 0, 0, 0, 1, 1. And then again, same thing, 1, 0, 0, 0, 1, 1. And then we add everything together. So these 0 just then drop down. Now 1 plus the rest of 0 is going to give you a 1. 1 plus the rest of the 0 is going to give you a 1. 1 plus the rest of the 0 is going to give you a 1. All of these will give you a 0. 1 plus a 0 will give you a 1. Now the only ones that's going to be carried is the one in the front. So we would start with these first. So 1 plus a 1 is a 0 with the carry. 0 with the 0 is a 0. Then we're going to take that carry and add it to the top line. So a 1 plus a 1 is going to give you a 0 with the carry. 0 with a 1 is a 1. A 1 from the carry plus a 1 is a 0, again with the carry. And then that carry would just drop down because it's assume a 0 underneath that. So there you go. Questions? Okay, so we're okay with multiplication for binary. So the next part we're going to talk about is going to be your hexadecimal conversion. Like I said, hexadecimal is used in addresses, like your computer address. IP version 6 uses hexadecimal. The physical address of your system, which is a MAC address, that uses hexadecimal. Hexadecimal is used in memory address. So when you work with like assembly program, or sometime when you get when you're looking at like a memory location, it would be, depending on the architecture, of course, it will say like X00, A4, B, etc. So hexadecimal, we want to be able to understand how that's compared to your decimal or your binary value. And it is base 16. So to reference this, you can also go into your notes. And last time we talked about size, right? And in storage. So in development, you would often think about how you can effectively and efficiently use your memory or your storage. Okay. Because there is a limit to the amount of storage that you can allocate for your application. So a byte ultimately is 8 bits, and that will be 8 binary, right? Digits that you would see to represent the byte. There are 256 different bytes that can represent in the integers 0 to 255. And this is why when you look at, if you know networking, when you look at it, like the subnet mask, you would see either 0 or 255. Okay. Then for a word, we mentioned last time that your word in general, and it doesn't always, stay as a size. So a word can also be, here it says 32 bits or 64-bit, but for Microsoft systems, like also Intel basic system, it uses a word size as 16 bits. So a word is just a basic unit of storage that depends on the type of processor. So think of it as just a way that we can represent a unit of storage overall. So instead of saying 2 bytes, we would say 1 word, or it's 4 words, is going to give you 64 bits. Okay. All right. And here it talks a little bit about ASCII, and that's just going to represent the 7 bits in the byte, 0 to 127. Because above that, even though I think you can expand above 127, and we'll come back to this with the ASCII table. Mainly that's going to get into the symbols. Okay. So the encoding process or the encoding system can be different for different type of applications. In general, we would see ASCII or Unicode being utilized, but you know, we can't assume that all application would use the same type of encoding system. So encoding just means what? A certain symbol or character can represent a numerical value. So for example, like if you're familiar with ASCII, 65 would be equal to an A. So that means that 65, the value 65, that numerical would be equal to a letter A. Okay. So it's just a way that we can represent a character as a value. Because remember that your computer is a calculator, and all the text that you enter, it needs to compute it, it needs to calculate it. So when you type things in, the computer sees everything as a number in binary. Okay. So hexadecimal is a base 16. We already touched on base 10 and base 2. Now we're going to get into base 16. And I know I put this in your assignments as well, but I'm going to pull it up so you can see. This is a table that you can see the equivalence of what a hexadecimal value is to a decimal or a binary. So when you have the decimal number 0 through 9, it's exactly the same in hexadecimal. But when I have a number 10 in decimal, in hexadecimal, it will be A. 11 in decimal, hexadecimal will be B. So when I give you a hexadecimal value B, you know that that will be 11 in decimal. C is going to be 12 in decimal, D is going to be 13, E is 14, and F is 15. And that would conclude the entire number set for decimal, hexadecimal. There 16 number, and that's it. Okay, so there's nothing beyond F. It's only between 0 through 9, A, B, C, D, E, F. That's it. Okay. So when we look at this example, this is A to 16. Just like the binary, the least significant bit is on the rightmost hand side, which is the 2. Okay. There are several ways that you can convert hexadecimal. This method is shown in multiplication. Okay. So the first digit on the right, you would take that and you would multiply it by 16 to the 0 power, because that's the least significant digit. So anytime that you raise anything to the 0 power, that's equal to 1. So I can have 1,000 to the 0 power, that's 1. I can have 20 raise it to the 0 power, that's 1. I can have 1 raised to the 0 power, that's also 1. Then as you move to the left digit here, which is an A, and an A in decimal is 10. So what we're doing is we're going to take the 10, which is decimal equivalent of the A, in hexadecimal, we're going to multiply it by 16 to the first. So as you move left, you are going to increase the exponent by 1 when you multiply it by the base 16. Okay. So once you multiply everything out, you would add it, and that's going to give you 162. So when you go from hexadecimal to decimal, then you can use multiplication method. Okay, there's another approach. So I'll show you another approach. So as you look at the second example here, as we have more digits, and each of the digit you would multiply it by 16 to the n power, and as you move left, that exponent value is going to increase by 1 each time. Okay. An important thing that I want to point out is each hex digit is going to be equal to 4 bits. So when you take a look at the first example, right, A2 in hexadecimal, that's going to be a byte because the 2 takes up 4 bits and the A takes up another 4 bits. So that's going to give you 1 byte. In the second example, we have 1, 2, 3, 4, 5, 6 digits in the hexadecimal. So we have 1 byte here, 2 byte, 3 bytes, or 24 bits. Okay. And half of a byte or 4 bits is, its name is a nibble, which is half of a byte. So a byte can represent 2 hexadecimal digits. Okay. All right, so I'm sorry, this was 24. Did I say 32? I apologize. This is the 24. 4 times 6, it should give you 24 bits. All right, so let's take a look at your assignment. Okay. We are going to convert 2A, and 2A is in hexadecimal. This is, it has a little base 16. The subscript 16 tells you it's a hexadecimal. And we wanted to make it into a base 10, a decimal number. So you are going to start with the most right. Okay. And that is going to, I'm sorry, which is a B. And I know that a B is equal to 11 in decimal, right? So if we start with the most right, I'm going to go ahead and type that. That will be 11. The conversion would be 11 times 16 to the 0 power. And that's going to take care of our B. Okay. Then what we want to do is we are going to take this and we are going to add it to the next digit. And I'm going to go from right to left. So I'm going to add it to the left so you can see. Then the next digit is going to be 1. Okay. So we are going to take that 1 because 1 in hexadecimal is equal to 1 in decimal. But because it's the second digit, it is more significant than the previous. So we're going to multiply it by 16 to the first power. like and then now we are going to add it to the next digit, which is 2. So then here I would take 2 and I would multiply it by 16 to the second power as I'm moving left. I'm going to increase the exponent. Okay. Then you can multiply everything out and you would get your result. So 16 plus 11, 16 to the second power. So if we want, we can pull up our calculator. We can go to scientific mode. So 16 raised square that, that's 256 times 2 plus 16 plus 11 is going to give you 539 with a base 16. I'm sorry, base 10. Okay. Any question? Okay, now you know how that's done. You can try number 2B. Start with D, and then that will be multiplied by 16 to the 0 power, and then plus 3 times 16 to the first, plus 9 times 16 to the, and so on. And then once you have everything written out, then you can multiply and then add, and you would have your result. Question? Okay, so make sure that we complete 2B. Next, we're going to talk about converting converting decimal to hexadecimal. So in the notes on the bottom of page 6, you will find an example. It shows you here that to convert 7562 in decimal to hexadecimal, we would use the division method. As when we go from hexadecimal to decimal, we multiply. From decimal to hexadecimal, we divide. Okay. And you would divide it by 16. Why? Because it is a base 16 number. Hexadecimal is a base 16 number. So you would start just like what you did with the binary. You would start with the decimal and you would divide it by 16. You would get a quotient, but I want you to keep the remainder noted because that's going to be your result value. Okay, so if I take 7562 divided by 16, I would have 472 as a quotient, and the leftover is going to be 10. And that 10 is A, because decimal 10 is A in hexadecimal. Then I'm going to take the quotient again. I'm going to divide it by 16. That's going to give me 29 quotient. And I should have an 8 remainder. And 8 is an 8 in both hexadecimal and decimal, so you make a note of the 8. I still have 29, so I'm going to go again, take 29 divided by 16. I have 1 for the quotient with 13 as a remainder. Then 13, in decimal, we can convert that to hexadecimal as a D. So note that this 1 in the quotient, we're not done. We have to get it to 0. So we would take 1 divided by 16. You have a 0 quotient with a 1 remainder, right? And then you make a note of that 1. Because if you stop like at that 1 for quotient, you're early. You're not complete. It's incomplete. Okay. So once we have the remainder noted and we got to the 0 for the quotient after we divide all those steps, just like the other one, we're going to record. So the bottom is going to be the most significant bit. It's going to be the left digit. So it's going to be 1. D is the next one. D, 8, and A. So the remainder for the first round of division is always going to be the least significant bit, the most right. So you're going to go from bottom up, left to right. Okay. Question. I find that knowing how to do long division is very helpful in this particular case. Okay. So let's do one together. It tells you to do number 3, convert the decimal values or value 801 in decimal to hexadecimal. So let me clear my whiteboard real quick. So I have 801. And this is the base 10. I'm going to go ahead and divide it by 16. So, okay. So we would take the 80 divided by 16. That's going to give me what? 5. Okay. And then I would have 0, 0, 1, 1 divided by 16 is going to give me a 0 with the 1. Okay. So this is a remainder. Okay. Hold on 1 second. For some reason, I thought I had typed this out. Okay. Okay. We're on the right track. All right, let me share that again. Sorry. It's been a long day. Okay, so 50, again, we are going to divide it by 16 again, second step. We are going to take 50 divided by, okay, so that's step 1. Okay. Then we are going to go again with step 2. Okay, so I'm going to take this quotient 50 and I'm going to divide it by 16 again. Okay, so 50 goes into 16 how many times? 3. Okay, and 3 times 16 is going to give me 48 with the 2 remainders. So I'm going to have a 2 as a remainder. Then I'm going to move to the next step and make sure that I keep the remainder recorded because that's going to be the value, right? So the next step is step 3. We are going to do 3 divided by 16. And since it's less than 16, it's 0 power with the 3 remainder. Okay. And since our quotient is 0 now, we're done. So the way that we record it, right? Bottom up, left to right. So we would have 1, 2, 3, base 16. And you can check if I punch in decimal 801, right? And my hexadecimal 3, 2, 1. Question.
Professor,
Yeah.
I'm just a little confused about the remainder parts.
Mhm.
'Cause,
So
I don't know, I'm just confused about those.
how did I get the remainder?
Mhm.
Okay. So instead of rewriting it, I'm going to show you. So I did some shortcut there, but let me erase this. Okay. So if I take the 801 divided by 16 using long division, it will be 50 for the quotient because 50 times 16 is 800. And if you take that and you subtract, you should have a 1. Okay.
Oh.
It's a long division process. Okay. And then if I look at the second step, if I take 50 divided by 16, it's 3 times because 3 times 16 is 48. And I subtract that, I should have a 2. So 2 is the remainder. Okay. And anytime when you get toward the end, anytime that you have the number right here, okay, this one, if it's lower than the number that you're dividing, it's always going to be the remainder because it's less, right? So 3 divided by 16, it's 0 times. 0 times 16 is 0. If you subtract that, you're going to get a 3. It's going to be a 3 as a remainder.
Okay.
Yeah.
Okay, thank you. I get it now.
Okay, good. Other questions? So long division works well here because if you punch it into the calculator, it's going to give you a bunch of decimal and then you have to figure out the decimal, what that value is. So if you need to do the decimal to hexadecimal conversion, using the division method, do the long division so you can see the remainder. It's clear. Okay.
Professor Nguyen,
Yeah.
the final answer would have a base 16, correct?
Yes.
Okay.
So when you write it out, yeah, you would put the base 16. So in the calculator, it tells you this, right? But because it's hex right here, so you would have 3, 2, 1, and then base 16. So we would keep dividing until we get 0 as a quotient. That's when we stop. Okay. All right, so what I want to do is I want to show you how you can do this in binary. There are different methods in it, but since we talked about how each hexadecimal value is equivalent to 4 bits, right? So let's take a look at the next one. So when you don't use the 4-bit conversion system, what will happen is you have to convert the hexadecimal to decimal and then from decimal to binary. It's just too much, right? So what I like to do is I like to take a look at number 4 and I say, okay, each of those digits represent 4 bits. Oops. So let me clear my whiteboard. And so I'm going to start out with B61 base 16. This is my hexadecimal, and I need to make it into a base 2. So you would start with the most right, of course. Okay, so I would start with this right here. And remember the scale that we went over for binary conversion, right? So our scale would be 1, 2, 4, 8, 16, right? But since a hex is only 4 bits, we can stop there. Okay. So what would represent a 1? That bit is on, the rest is off. Right? Remember the subtraction method? So, or you can do the division. So in a 4-bit representation of a hex 1, it's 0, 0, 0, 1 in binary. That's easy. Then next, we're going to take a look at the 6. It's also 4 bits. So again, I would put my scale 1, 2, 4, 8. Oops. What adds up to be 6? A 4 and a 2. Okay. So 0, 1, 1, 0 would represent a 6. And then lastly, we're going to do the B. Again, I put my scale 1, 2, 4, 8 because we're going to go to binary and it's a base 2. So it's multiple of 2. What adds up to be a B? So we know that a B is 11 in decimal. So we look at the scale for the decimal. What adds up to be 11? 8, 1, and 2. So B61 with the base 16 is equal to 1, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 1. Base 2. Okay. So in the 3-digit hexadecimal, that's going to give you 12 bits. Much easier than division, going to division multiplication for decimal conversion, right? Hex to binary is super easy. Any question? Yeah, so this right here, this is just a scale. This part right here, remember the table that we use? This is a decimal equivalent scale. your answer is this. So because we are gonna go from hexadecimal to binary, and binary has multiple of 2 decimal equivalent, we need to place the binary scale there. I mean the decimal scale there to be able to look at the value that will be equivalent in decimal. Okay. Yeah, I always write the scale there so I can quickly see it, but if you can do it in your head, that's fine too, right? There are tables and we don't need to memorize the table. You just know it's multiple of 2 and that's how it would represent it. So if I have, like, for example, if I have like this, right, you would know that it's 2, 1, I'm sorry, it's 1, 2, 4, 8. If you add this up, it's what, 10, 15, it's 15. So for a hexadecimal, it's 16, right? 16, it's a base 16. So that's going to lean into the next nibble as, you know, that's why it's 4 bits, because if you add up the decimal equivalent, this is equal to 15. And it's 0 to 15 for hexadecimal for the 16 number base. Okay, so you will be expected to know how to do the conversion in hexadecimal to binary, and then, you know, going vice versa, or you would be expected to also know how to do decimal to hexadecimal and going the other way. So your question to me should be, how can we go from binary to hexadecimal, right? You can chunk it up into 4 bits like what we just did, or you can convert it into decimal and then from decimal to hexadecimal, which is a longer process. So break it up into 4 bits would be easy. Okay, any question? So you can do number 5, starting with the 2, make that a 4-bit, starting with another digit C, another 4-bit, and so on. And for the C, make sure that you remember that a C is 12 in decimal, and which bits add up to be 12? An 8 and a 4, right? So it's 1 0 1 0. I'm sorry, 1 1 0 0. I was thinking of 10. Question. So make sure we complete number 5. And then I'm going to do the octal with you. So octal system is really, this was used for older systems, right? Back then, the way that storage was used was limited. So you don't have as much storage as what you've seen today or even before that. So what you have is you would have like a 6-bit bytes, and the 6-bit byte can be conveniently written into octal digits. Okay. Nowadays, we just use a byte, and then that would represent the 8 bits. But I want to show you this, and any time that you need to work with octal system, you would know how to do it. So octal is a base 8. Okay. So just like how hexadecimal is a base 16, octal is a base 8. It just have less numerical values. So you can use the multiplication method like what we learned in hexadecimal to decimal conversion, but instead of multiply it by 16, you will multiply it by 8 to the power of n as you move left. Okay, so this example kind of show you how that's done. Also, we know that octal consists of 3 bits. Like how earlier I showed you the hexadecimal is 4 bits, octal is 3 bits. Okay. So when you look at the 23, you would break the 3 and represent it in the 3 bits here. So it will be 1 0 1 1 that would represent the 3, and 0 1 0 that would represent the 2. So chunk it up into 3 bits, like how we chunk it up. We chunk up the hexadecimal digits into 4 bits. So let's try number 6, A and B and C. So I like to do this with binaries. It's just my preference instead of like dividing everything out and find the remainder. You can definitely do the division method, going from decimal into octal, just dividing by 8 and then note the remainder. So you can do it that way, or you can convert 124 into binary and then from binary into the octal. Okay, so if you want to check, we can always start with looking at what that would be like. Here is the octal, so it tells you it's 4 4 4. So what I can do is I can illustrate both if you like, or we can go with one method. So I'll start with making 124 into binary. Okay. So we would start with we would have 1 2 4 16 32 64. And I don't need to put 128 because I have 124. It's less than 128. So we can subtract it as we go down the line. So turn this bit on, 124 minus 64 is going to give me 0 and 60. And then I subtract 32 again. So 60 minus 32 is going to give me 28. Subtract 16. That's going to give me what, 12? And then, so that's that. So 12 subtract 8 is going to give me 4. 4 subtract 4 is going to give me 0. I'm just double checking my math, making sure. 0, 16. Okay. Oh, I'm off. I was like, why is that not right? 124. I gotta make sure that I select. Sorry. Okay. Okay. So now what we're gonna do is we're gonna group them by 3 after we convert it into that binary. So we're gonna go here, right? And then, so that's gonna give you a 4. This part is equal to a 4, right? Because it's 1, it's 0 off on the 1 and the 2, and then it's on the 4. And then again, I'm going to chunk this up into another 3 bits. So it's 1, 2, and 4. So that's going to be a 7. This is a 4. And then on the left, that will be 0 and 0 here. So it's going to be again 1, 2, and 4. And so that's going to give me a 1. There you go. If you're looking at the octal. Okay. So in this method, what we did was we take the decimal, we convert it into binary, and then we chunk up, 3 bits for the binary to represent each of the digit in octal. I will illustrate the 6B in the division method so that way you know how to do that, just like how we did it with the base 16. Question on this? Okay, no question, huh? All right. Clear? 6B asks you to convert 62 decimal into octal. So we can do the division method, 62. And we simply just divide it by 8. So, but for 7 with the 6 remainder. I shouldn't do a shortcut like that. Hold on, let me. So 7 times 8 is 56. Subtract that, you should have a 6. That's the remainder. Since we still have the quotient there, the next step is we're going to take we're gonna take 7, we're gonna divide it by 8, which gives us a 0. 0 times 8 is 0. Subtract that, you should have a 7 as the remainder. Okay. And so when you use the division method, just like all the other ones, your remainder is significant. That's going to be your result. So you can't regard it. The quotient is just gonna, we just, as long as you have quotient left, you're gonna keep dividing until you get to 0, but ultimately your remainder is what your outcome will be. Okay, and then if you want to check your this to make sure, so if I have a decimal of 62, I would have an octal of, guess what, 76. There you go. So that there are 2 ways to approach this, whichever that you prefer. You know, you can take the decimal, put it into binary, and then chunk it up into 3 bits each. And you should be able to see the conversion there on how that will be in octal, or you can take the decimal divided by 8 and then make sure you note the remainder, and that's what you would have for octal value.
Professor Nguyen, I'm not seeing where the 6 comes into play here. How is the answer 76? I mean, I get the 7, but
6 is your remainder.
so we're just combining
So-
it together.
So when you take 62 here and you divide it by 8, 8 times that will be 7 times,
Right.
right? And so 7 times 8 is 56. You take 62 divided minus 56. This is your remainder, 6.
Yeah, no, I understand that. So
Yeah. So you as long so this is the first digit, right?
okay.
That's the least significant bit.
Oh,
is
that's
your-
right.
Yeah.
If you're on the least significant, okay.
Yeah. And then as long as you have quotient, you got to keep going again. So
Gotcha.
if I have like 6002, I am going to keep dividing. So I would have many digits.
Right. Okay, that's the concept I'm trying to wrap my head around. We keep moving left from the remainder.
Right. Because this culture is, we read English left to right. We see things left to right.
Right.
But yeah, but the way that our system is designed is right to left. So yes.
Now it makes
It grows leftward, yes.
Thank you.
Other questions? Good point. So either technique that you use to solve these, you should have the same outcome. Okay, that's my point. Is if you use the binary method, like you would convert it to binary and chunk it into 3 bits each, it should give you also the same output as the other one. Because math, how you solve it, right? As long as you use the proper, the proper technique, you should get the same outcome. Okay. All right. So that is 6. And then on this one, they already give you the binary. So what you should do is you should chunk up each of these into 3. And then if it's missing 1 digit, just assume that it has a 0 in the front like that. Okay. I should highlight it in a different color so you can see it. I'm a very visual person, so yeah, sorry if you see all these colors on my notes, is because that's how I learn. That's how I really see stuff. So when I learn math and things like that, I would make it easier for myself. But some students, they prefer it that way too. So then you would then just convert this. So that will be what, a 1 1, 2, 4, so that's a 6, a 5, I'm sorry, a 5, right? A 7 and a 1, 2, 3. So 3, 7, 5. Okay, so once you chunk it into 3 bits each, you would put the little scale on the bottom, starting from the right, like 1, 2, 4, and then again 1, 2, 4, and then again 1, 2, 4, and you add up the bits that have the ones, right? So this one would be like the 1 is on, the 2 is off, the 4, so that's a 5. This is a 5. And so on, and you would move forward, move left. Question. All right. Disregard that for now. Okay. The next part we're gonna touch on, and we still have time. So if you feel it is too fast, if you need me to go over something again, I'll be happy to do that. Because sometimes the stuff takes a little bit of time to digest. Okay, and you can practice more. I think in your book it shows example. There are some exercises that like could be at the end of the chapter. So
For C, Professor Wynn, would we need to put the sub 8 for the answer?
yeah,
Okay.
yeah. If you want to put the subscript 8, sure. It is helpful because when you have like different number system together, you want to distinguish them. So yes, that will be helpful because it's 0 through 7 for octal. So all right. The next part we're gonna touch on is gonna be 2's complement. Negative number. So, like I mentioned last time, the computer only adds, okay? It adds, so if I have, a 1 plus a 1, it converts the decimal 1 to the binary and then the other 1 to the binary and it adds it and it's gonna give me, it has the binary converted back and it's gonna give me a 2. Now, when you subtract, it's gonna take let's say I take 4 minus 2, it's gonna take the 4, the positive 4, it's gonna add it with the 2's complement or the negative 2. So when we say 4 minus 2, it's like saying 4 plus, right, negative 2. So the way that we represent the negative number is the way the system represent the negative number is using what it's called a 2's complement. And as you saw in the last time that sometime when you have a negative value, like in your calculator, right? So let's say that if I have a negative 23, if I look at the binary, you see all these ones in the front, it represents the negate, right? And so it would say that a single bit is used to represent the sign of the number, a positive or a negative sign. So it reserves that 1 bit to store what human calls as positive or negative sign. Now, when you learn C++ or a programming language, right, especially C++ or C, you would see that when we type the data, sometimes you see program that would say unsigned and sign. So when you have a sign in the type, you know that it stores negative. Okay? So in programming, we would refer to a negative value as sign. And unsigned is a positive value. Okay. And here it says that the remaining of the bits to represent the magnitude of the number, how positive it is that would be the remaining of the bits, right? The value of it. So 2's complement, we would then need to really see how the system see a negative number. Like what earlier when I type in -23, how does it really take that value and convert it into what it would store? So the step of doing this is that you would make everything into a binary, right? Like hexadecimal, you got to put it into a binary, but there is also a method to do hexadecimal complements. But so if you have a value, the first step is to convert it into binary. Then the second step is to apply the logic not, or the opposite of that bit. Okay. So let's say that I have a binary value, then I'm going to flip the bits. The ones are going to become the 0 are going to become the 1s. But wait, I'm not done. After I apply not operator to it or flip the bits, I need to add 1 to it, because remember that 1, when you add it, it's use it to store your sign. Okay, that 1 bit is used to store the positive or the negative sign. That's why you add the 1. Okay, so in this example, here is a decimal 3. And decimal 3 is, here's your binary. Okay, a 1 and a 2 gives you a 3. And that 0 in the front right here, right? This bit in the most front, we earlier we said, oh, that could be the most significant bit. But this bit in the most front, right? And could be some of the following bit. It's going to fill that in. That's going to be used to store the sign. Okay. So if we start with the decimal 3, and if we wanted to make it into a -3, we convert it into binary. Then we are going to flip the bit. So you're going to use the operator not. So the 1 here becomes the 0. And then the 1 next to it becomes the 0. And then the rest of the 0 becomes the 1. Okay. That's what we call the 1's complement. Now to really sign it, then we're going to have to add just 1 to the binary value. And that's going to make it a -3. Question. Let's try together our assignment. There it is. Let's do A7A together. And I think that's it, right? Yep. Okay, so for 7A, we have 89 in decimal, and we want to make -89, right? Representation for the system. So we first need to convert it into binary. So step 1. So I write out my scale. Okay, and I don't need to go further because it'll be larger than 89. So I'm going to use the subtraction method. So 89 minus 64, right? I put a 1 on top. That's going to give me what? 5, 25. It's 25 is less than 32. I'm going to put a 0. 25 minus 16. That's going to give me what? 9. Then 9 minus 8. That's going to give me 1. So I would 0 these out. And 1 minus 1. That's going to give me 0. So, right. Okay. So step 1 is to make our decimal into binary. Okay. Any question? Then the next step is we're going to flip the bits. So I'm going to go ahead and erase all the subtraction because I need the space to show you. Okay. And then I'm also going to clear this out. So step 2, we are going to apply the not operator. So technically we're doing this. Which is equal to opposite of it, right? So 0, 1, 0, 0, 1, 1, 0. So how did I do that so fast? The 1 here becomes the 0 over here. And then the 0 here becomes the 1 here. Because you nodded. And we will talk about logical operator next time on Tuesday. So once you flip the bits, you get the opposite of what you started with. Then you are at the ones complement. Then we are going to move into the third step, which is now we're going to take the result from the ones complement and we're going to add 1 to it. So 0, 1, 0, 0, 1, 1, 0. We are going to add it with the 1. And simply, right, 0 plus 1 is going to give me a 1, 1, 1. Okay. And in the system, it would then, so if you're using a quad word, 64-bit, then the rest of the front would be using the bits in the front that would be representing the sign, but it's only going to store that sign in only 1 bit. Question. So this shows you how you can do the 2's complement. You can try B. So make 161 into binary. And then from that, what you can do is you can flip the bits, then add the 1, and you would have 2's complement. I will do C with you. And then, so you are to do B and D on your own, okay? I have a chat question. There are only 7 digits. Need to add a 0? Yeah, you can, because when you add more 0 in the front, right, to represent the byte or even larger, when you knot it, it becomes a 1. Okay, so what do I mean by that? Okay, so let's say that this is our binary to start. If we add the 0 in the front right here, when you knot it, right, you also going to have a 1 in the front. And all of the imaginary 0 over here is going to become the 1s too. And so therefore, when you look at this, right, it was 89. If you put a negative in, guess what? Okay. So yes, I suggest putting the 0 so you can actually see the effect of the negate in the front. But you don't have to do so many. Yeah, so that would be a byte. Okay. And so the answer for this would be this, right, with a bunch of 1s in the front. You're welcome. All right. Other questions? We still have 30 minutes. So the only last thing that I'm going to probably do is do C with you, and then you can do D.
Professor, I have just a quick question for clarity.
Okay.
So when we say the 2's complement, it's the step after the flip, I guess.
Uh-huh.
So if the question is the 1's complement, then it's just the not operating process. Okay.
Yeah, so to really represent a negative number, it has to be 2's complement.
Oh,
Because as you negate it, that 1 bit that you add, it stores the positive negative sign.
okay.
Okay. Yeah, because if you don't add that 1 bit, it's incomplete. It can't show you whether it's positive or negative.
Okay.
Uh-huh.
Thanks.
You're welcome. So now in some classes, let's say that you transfer after the semester or a few semesters from now, when you go to university, the class that need to reference this material, they would assume that you know how to do this already. So if you don't know how to do 2's complement, so those classes are what, digital, which is required in computer science, assembly, which is CIS 11 at RCCD, depending on, so I re-emphasize this in 11 because in assembly, when you program the instruction, you clearly see this. You clearly see why, like, you need to add on that 1 bit to really hold a negative value for the, using the low level instructions. Okay. All right. Other questions before I do the C for 7? Okay, so for C, we'll just use the whiteboard. 1 0 0 1 1. I'm usually happy when I see binary, right? Because it saves me a step in most part. And if I can, if I have a binary, I can make it into any number system, knowing how to do decimal or even hexadecimal, right? So it's super easy. So Next, so I already have step 1 established. Then I simply make this a 1's complement, okay? By just flipping the bits, by not it, right? So let me switch pen. So the 0 becomes, I'm sorry, the 1 becomes the 0, and the 0 becomes the 1, the 0 becomes the 1, the 1 becomes the 0, the 1 becomes the 0, the 0 becomes the 1, the 0 becomes the 1, and so on. And then now I'm going to move into the 2's complement by just adding that with a 1. So now we're going to have to do the carry, right? So think of it like you adding this. So what we're going to do is we are, oh, sorry, I tapped my fat finger that. Okay. A 1 plus a 1 is going to give me a 0 with the carry, right? A 1 with the 1 is a 0 with the carry. A 0 with the 0 is a 0. A 1 with the 1 is a 0 with the carry. A 0 with the 0 is a 0. A 1 with the 0 is a 1. A 1 with the 0 is a 1. I'm done with the carry at this point. A 0 with the 0 is a 0. A 1 with the 0 is a 1. A 1 with the 0 is a 1 and a 0. So that's my 2's complement. So in some case, when you add that 1 bit, it's not always clean, right? It has some carry. So just make sure that you line it up and you add it. If the back digit here is a 0, that's really easy because that 1 bit only changed that to a 1, but it will not be if that least significant bit is a 1. Then we want to make sure that we carry everything in, make the addition properly, and you would have that for the 2's complement. So you will be expected to know how to do 2's complement and okay, and conversion for hexadecimal, octal, multiplication, addition, subtraction for binary, and binary decimal conversion. So since we already saw how C is done, I show you how that's done. You can do question 7D. You have the binary, you just need to knot it for the 1's complement, and then you add the 1 bit for the 2's complement, and you're done. This class is pretty easy for most part. And so, you know, you want to expand. I don't want to do like a lot of heavy duty math theory stuff and then that gets lost. So I'm just aiming for the objective of the course outline and the discrete and how you can apply this for the programming and for your field, and so that way you can just expand on your skill. Okay. Question. So after you take this class and you take assembly and you learn programming, everything is going to gel together. It's going to make a lot more sense. Computer science is one of the harder area, but everything's gonna glue together for sure. I promise. All right. So if you have time right? We don't have any homework. So if you finish everything, you can upload it, submit the assignment. And so that way I can grade it, but this is not due until Sunday. So if you want to spend a little bit more time on it, you can. Okay. And have some time. You can read the next couple of chapters. We'll, 2 is going to go into logic gates. And then we'll do some, some logic operator like and, nan, not, or, etc. Okay. So in the next chapter, we will work on the logical operator and logic gates. And then we will program some of that. Okay, using C++. And then the following week, we're gonna hit sets. So we'll start with sets and then move from sets into counting. Question.
Professor,
Mm-hmm.
I was on 6A. I had to go somewhere real quick, so I wasn't able to see you work that problem out for 6A.
Okay. Yeah, I can redo that.
Okay, thank you.
Yeah. Okay, so for 6A, we have the octal 120, the decimal 124, and we want to go into octal, right? So the way that I did this, there are two choices. You can convert decimal into binary and then from binary into octal. Or you can do the division method and you would be able to convert from decimal to octal. So I'm going to do the binary method because I showed the other method with the division for the next one. All right, so let me see if I'm on that pen. What was it, 124? Okay, so 124 in decimal, right? Here is where I'm going to convert the binary. So I'll just put this aside here. So 1, 2, 4, 8, 16, 32, 64. Okay. And then I would take 124, subtract 64. So I put a 1 at the top. And I'm using subtraction method to go from decimal to binary. So I should have 60 left. 60 subtract 32. Then I should have 28 left. Then again, I would take 28, subtract 16. And as I subtract, I put the 1 at the top. I should have 12 left. 12 subtract 8. I should have 4 left. Then 4 subtract 4. I should have 0 left. And I just fill in the 0 here. Okay. So right now, what I did was I put the scale for the decimal equivalent to the binary so I can convert it into binary. Then after that, I would then be able to take the binary and make it into octal. Easy by chunking it into 3 bits. So I'm going to rewrite the binary again so you can see. So it's going to be 1, 1, 1, 1, 5 ones and 0. Okay. So now what I'm going to do is I'm going to chunk this into 3 bits each. And if there's that 1 hanging in the front, you can just simply add the 0 in the front, right? And octal is a base 8. There are only 0 through 7 as the value. So what you would have next is I would then put a little scale down here. So 1, 2, and 4. 1, 2, and 4. 1, 2, and 4. Because that's my decimal equivalent, right? Because remember, I start with the decimal here. So I know that this chunk, this 3 bits, the 4 is turned on right here, this one, right? So then that will be a 4. And then on the next chunk, which is 3 bits, I have a 1 and a 2 and a 4 turns on, and you add those, that's going to give you a 7. So a 4 here, a 7 here, okay? And then the last one on the left, the only bit that's turned on is that 1. So you are going to have a 1, so 1. 1, 7, 4, base 8. Okay, and this method is to take the decimal to the binary, chunk the binary into 3 bits, and then convert it into octal.
Oh, all right. Thank you.
You're welcome. The 6B, what I did earlier was I illustrated by using division. So you can take 62 divided by 8, the remainder, take the quotient divided by 8 again, right? And then the remainder is going to be your octal value.
So, Professor Wynn, for turning in this work, just for clarity, do you want us to show work or just turning in the document is okay?
You can type in the document, do your best to show the work. I know that I realize that you probably use scrap paper or whatever to calculate. I'm fine with you know, with you typing out your answer without all the steps. Your assignment is really designed for you, okay? So whatever that you would understand it best, that's how I'm gonna take it.
Okay.
So if you are thorough, you want to type out everything, because I don't know, a month from now, you need to know this for the quiz. You can go back to it, look at it and say, oh, that's how I solved that problem. Okay. But some student, they just type out the answer. I'm okay with that too. And I assume that you would know how to do that if you just type out the answer.
Okay.
Okay. I'm not your traditional math faculty. They probably watched my video and said, this Casey. But so I know that they want you to improve, like they want you to show every step, right? I took calculus, I took advanced math. So it's really designed for you. So the more notes you put, good for you. Type out the answer. If you hand wrote everything like what I've been doing just now, you can take your phone, use an app, scan it, or take a picture of it. You can submit it that way to me too. Okay, if you don't have a scanner at home, I'll take that. As long as I can see your answer. Yeah, I had some student for semester now that they use it that way, and because I understand that not everybody have scanner or have access to certain resources. I don't want you to have to go to like those places where you have to pay to scan for things. But our lab is open. I think they do charge you for using copier and scanner. Question. Okay, it is at the end now. So if you finish, don't forget to submit the work. You can spend a little bit more time on it if you like. You can type your name into the chat so I have a record of it in case we need to reference attendance. And have a wonderful evening. Okay, I'm going to stop recording.